say a word. Welcome, students, to the afternoon session of the last day of the school. We have Professor Badri Krishnan giving his third and last lecture on theoretical aspects of black holes. Over to you, Badri.
Okay, good. Thank you, Surya. So let me first, so today we'll talk about dynamical black holes, and in fact, we'll talk about, observational tests and also numerical results. But before all that, let me just complete one thing which I in fact forgot to mention last time, which was the calculation of the horizon angular momentum. So last time I gave you a formula which used this one from omega, if you recall. So this was this one form which appeared when we defined these weakly oscillator horizons, and we defined through a Hamiltonian calculation what the angular momentum was at the horizon. And this result used this quantity called omega, which is fine, but it's not really practical in terms of applications to numerical relativity. So let me just explain that here briefly before we begin the main talk for today. So the framework is in numerical relativity. Typically, it is that you have a given spatial slice. So this is a time equal to constant surface in your simulation. And on this surface, you have the extrinsic curvature that is referred to here as K. And you have the 3 metric on this spatial slice that is referred to here as H. And if you have any surface here like S, you can define these null normals to this surface using these definitions here. So first of all, we have the vectors t hat and r hat. So t hat is the unit time-lag normal to this surface, and r hat is the unit space-lag normal to S within sigma. Okay, so you have a given surface. There's one direction which goes out of it, that is this t hat. So it's unit time-lag. And you have within the surface, you have unit space like radial vector r given to you. So from these two, you can construct the L and the N. So this is one choice of null normals. And it's not to say that this is the canonical choice, but in fact, it doesn't really matter. So once you have, even though when you define the angular momentum, it was for a weakly oscillator horizon which required, excuse me, which required a particular class of null normals. But in the end, the formula that you get is in fact independent of that choice, okay? So this is a nice thing, which means that we can in fact use already this L for all our purposes and this N for our purpose as well. So what is then done is that it is a very short calculation, in fact, to convert the formula we had before in terms of omega. And it leads to a very nice and convenient result, which is useful for numerical relativity, which is that you write the angular momentum of the surface S as this combination here. So it is the extrinsic curvature that appears here first. And this is the radial angular part of this extrinsic curvature. Okay. So a key ingredient here is this choice of phi. And there's a lot of discussions on how to choose phi, whether the horizon axisymmetric or not, and so on and so forth. But if you're given a phi which you believe for which you want to calculate the angular momentum, then this is what you should do. So you have the extrinsic curvature, contract. So sorry, this is r. So this is meant to be the this radial vector here, r hat. But anyways, it's a radial component of r and the angular component, and you integrate that with the proper volume element over S, and that result gives you the angular momentum. And then to get the mass, again, following the same equations like we had before, first of all, you want to compute the area from that you compute the radius of the horizon. So by radius here, we just mean area upon 4 pi and then the square root. And then you take that and you combine that with the angular momentum, and that gives you the mass. So this is then a very practical sort of procedure to compute the mass and the spin for a black hole in numerical simulations. And it is used quite commonly in numerical simulations. And so I want to talk more about the details of how you want to choose the phi and what are the subtleties associated with that. And our focus has been mostly on the theoretical aspect, which is the black hole thermodynamics and formulating the quasi-locally. But just so you're aware, so this is the starting point for a lot of work in numerical relativity. Okay, so let me conclude then the discussion of angular momentum here, and let's go on to dynamical black holes. So any questions here on this? In fact, already on yesterday's lecture and for today's, if you have any doubts, any remaining questions.
Any questions, students? Can you raise your hand? Any comments or questions? There are none at this stage, but maybe as we proceed there.
So let's proceed. So now let us go to a dynamical situation, and the important thing that we'll focus on is the area increase law. So if you recall, I sketched for you the proof of the area increase law for event horizons in the very first lecture. And then we saw that that proof depends critically on what are these focusing points on the event horizon and how you rule that out and so on and so forth. And how you then show the area increase law for event horizons. Okay. And of course, for the second lecture, when we talked about isolated horizons, so that's a situation in which the black hole is in equilibrium, so there's no infalling fluxes in that case. So in that case, the area does not increase. So the second law is then really not relevant in that situation. So, but in reality, there are cases, so especially when you think of two black holes merging, so near the merger, the black holes are not isolated, and the black holes do grow, and the area does increase. And similarly, if you have a black hole formed from the gravitational collapse of a neutron star, for example, so the black hole will grow initially as sort of the matter falls in and collapses. So to discuss the situations, we now need to go beyond isolated horizons, and we consider now the dynamical situation. So again, if you recall, we started the discussion of isolated horizon from, in fact, dynamical horizons, which were null, okay? So, but now we need to look at the non-null cases. So now the horizons could be space-like or time-like. And as we shall see, the space-like one is the most relevant one, though the time-like one also does appear during black hole mergers, and I'll explain that in today's talk. But the space-like one is in fact the most important, physically important case. And again, just to remind you of the importance of the second law. So this comes from a theoretical perspective on the connection between the area and the entropy. And so it's a big effort in different approaches to quantum gravity to calculate black hole entropy. And so and it's found to be proportional to the area. So therefore, increase of the area isn't connected to increase of entropy. And so but that's a different topic. So I won't discuss it here, just to emphasize the importance of this result. So what we want to discuss is under what conditions does the area increase law hold? What is observational evidence for it? And is there a quasi-local version of this law? So if you again recall on this last point, we said in the first lecture that even though we have a proof of the area increase law for event horizons, it does not mean that locally speaking, the event horizon is shown to grow when there's flux of infalling matter or radiation through it. And we talked about the examples like the Vaidya spacetime in which you had event horizons which were growing, even though there was no flux of anything crossing it. So this was in part of flat space, and we found event horizons there, right? So then the question is, if we do have a sort of a local or quasi-local version of the area increase law, can we find flux law as well? And for event horizons, we did find I did mention to you the flux law. That was a Hartle-Hawking formula, but that was only valid perturbatively. Then the question is there something valid sort of more generally and in full GR without making any approximations? So we'll talk about that as well. So let me first talk about now the area increase law from an observational setting, okay? And we'll talk about now binary black hole mergers here. So in this case, imagine now two black holes which merge and make one final black hole. So each part of the event horizon, I mean, there's only one event, the whole event horizon is just one surface, of course. And but each disconnected component will also have increasing area. So the same argument like before goes through. And so when the two black holes merge, so the area of the final black hole, so that's A final, must be bigger than the sum of the two initial areas at any earlier time. Okay. And even though I won't discuss it in detail here, it should be kept in mind that we, as physicists, often imagine event horizons are sort of smooth surfaces, and they're not. Okay. So event horizons are not differentiable surfaces. So anytime that any, let's say a particle of dust falls in, it leaves behind a little imprint as a crease on the event horizon. The same thing happens, in fact, also when black holes merge. So these are not generally nice differentiable surfaces everywhere, and they're sort of crazy examples in which you have nowhere differentiable event horizons. But anyway, the proof has been generalized for all of these cases, and what I mentioned in the very first lecture, that extensions of that also work. And so you can assume that for event horizons, it's quite now settled that mathematically that the area does increase in very, very general settings. Okay, so now let's go on to observational results. So in fact, this goes back to Stephen Hawking back in 1971. And the very first estimate for how much energy could be radiated in a binary black hole merger was due to Stephen Hawking. And he had the following argument. So you start with two black holes very far apart. So the initial total mass is then just M1 plus M2. So the black holes are far apart, so there's no corrections from binding energy and so on and so forth. So the total ADM mass is then also sum of the two individual masses. So the final mass, so now you have to be careful what we mean by the mass here. Of course, the ADM mass does not change. What is meant here is that what is left in the space-time after all the radiation is left. So this is what is called the final Bondi mass of the space-time. So this is taken to be MF, and this is relevant to the final black hole that is left in the space-time. So now the area increase law implies, again, as we said, that A1 plus A2 must not be bigger than AF. And assuming now that the initial black holes occur and the final black hole is also occur, and so therefore we can say that the area should be connected to the mass and the spin through this equation. So A1 is going to be M1 squared plus this combination, where chi1 is a dimensionless spin, which can be between -1 to 1. So this combination of the masses and the spins must be satisfied. Okay, so this is M1, M2, chi1, chi2, and then MF and chi-F here. So with a little bit of manipulation, you can convert this to a limit on the efficiency, which is what I mean by how much energy can be lost in gravitational radiation. So that is this particular quantity here. And you can work out that if you have equal mass non-spinning black holes, in fact, that this is bounded to be about 30%. So this is, of course, a very poor bound, as we now know. So the results from numerical simulations get you to be much below that. But still, this was sort of the first estimate of this efficiency. Okay. So then the question then becomes, well, now we do have actual observations of binary black holes. So can we turn it around? Can we say that from what we observe for binary black holes, can we set a limit on the area increase and possibly find violations of area increase? Okay, so the logic is going to be the same. So what you do is that, well, you from the early part of the merger, you compute the mass and the spin, do the same from the late part, and then you want to see if this equation is true, right? So before I do that, let me first tell you how not to test the area increase law, okay? So if you read, for example, the first detection paper where this event 150914 that you must have heard about in some of the other lectures, so that was reported, then you'll see in the papers that what they report is also the initial masses. So for the first black hole merger, so it was about 36 and 29 solar masses. The initial spins were consistent with 0, but you did have some estimates on the most likely estimates of them, so 0.3 and 0.46. And they also gave you the final mass and the final spin. So you might say, well, that's great. So can I not just take M1, M2, chi1, chi2, and MF and chi-F, go back to this relation and make sure that this is satisfied or not? you can do that, of course, and you'll find it's always satisfied, but this is not a test of that area law because of the following reason, which is that in this analysis, what was done was that M1 and M2 carbon chi2 are the things that are really measured, okay? And MF and chi-F were actually reported based on results from numerical relativity of simulations of binary black holes. So these were fitting formulas in which you obtain MF as a function of these initial parameters and chi-F as a function of these initial parameters. And in these simulations, of course, these are within GR. So by definition, then in these simulations, the area increase law should hold. So therefore, GR is not assuming that GR is violated, and it's a theorem within GR that the area has to increase. So it is, if you do find from this calculation that you violate this equation, the area increase law equation, then something has gone very wrong. It's just an error somewhere. So by definition, from these reported results, you cannot hope to test the area increase law by definition because this assumes GR. Okay. So what you need are independent measurements of the final mass and spins. So you have to sort of not assume that over the whole waveform that GR is true. You have to assume that independently, you have to independently measure the initial masses, initial spins, and separately measure the final mass and spins observationally. And then you can apply this equation. Okay, so then you're in a good shape that you can apply this and you can check for its violation or not, but not from these fits within GR. And in fact, I should say that this is just one particular case of a test between the initial and the final state of binary black holes. And these are generally, there's a number of consistency checks you can do in this scenario. So I won't mention all of them here, just to say that this is just one of these consistency checks that can be done. So this is the basic idea for the observational test. So as I said, so you measure the mass and the spins of the initial and the final black hole separately, directly from the gravitational wave signal. So this means that from the early power signal, in which the signal is an in-spiral signal, so it's a different scenario than for the final part, which is a ring down signal. And then once you have this initial final parameters, then you can hope to test the area increase law. And you assume that the black holes are initially and finally occur. That's a reasonable assumption. And you can weaken this assumption if you independently confirm that the final black hole is Kerr. So this would be, for example, where the ring down analysis comes in. So I don't know if anybody, maybe Paolo talked about the test of GR using the ring down. But in any case, if you do measure multiple ring down modes in the final part of the whole process, then you can in fact confirm that the final black hole is Kerr, or maybe it's not. And then you can sort of reduce one more assumption in this test of the area increase law. Okay. And then from all of these results, you can check that the change of the area, that delta A, is positive. But what you actually get in practice are not sort of point values, but distributions of all of these quantities. So therefore, you get a distribution of this change in the area. And then you can verify by calculating the integral within this distribution from minus or for negative values. So that is then the probability that the area increase law is violated, right? And then this is a quantifying this, you can use it to quantify how significant your test of the area of the test is. So now it turns out that in fact that most of the area increase happens during the merger itself. So the area does increase in the in-spiral phase, but only very little.
Hi, Badri. Just a request to use full screen. I think some text is getting tapped a little here. Present as slideshow. Yeah. Thank you.
Okay. Right. So now, as I said, so the area increase is, well, by the way, any questions up to this point?
Students, are there any questions? So maybe I have a question. For now, the discussion is for standard black hole horizons, right? I mean, but these are not arguments applicable to isolated horizons as yet.
It applies to everything, right? So as I'll say, so the distinction between event horizons and any of these local horizons is only there at the merger, right? So the early part and the late part, they're all the same. So in fact, if you measure the initial parameters, then it doesn't really matter if you consider that to be coming from the event horizon or from the isolate horizons, and similarly for the late time. So these observational results apply to both.
I
And
understand.
as I'll mention later, so the distinction between the two is important at the merger. Okay, so of course that's an interesting discussion, but at least observationally speaking, it doesn't really matter. So the area has to increase one way or the other. Could be through the event horizon, could be you might view the local horizons as more important, but whichever it is, the initial and the end points are the same, so it doesn't matter.
I notice Guillaume has a question. Guillaume, just unmute and speak, please.
Yeah, can you hear me?
Yes, we can.
Okay, very good. I was just curious about what you mentioned concerning nowhere differentiable horizons. So I guess it's a pure mathematical curiosity and it's not physically relevant, if you can confirm. And I would be curious to know who studied this and what was the motivation, or can you give a reference maybe, or say something? It's a curiosity question.
Yes, so the reference is by Piotr Krusiel. So there's a paper by Krusiel and Duncan and Greg Galloway on nowhere differentiable horizons. So their motivation, if I can speak for them, comes from the fact that event horizons are not differentiable surfaces in general, right? This is true, in fact, and physically speaking. And therefore, there's a question about the proof of the area increase law, whether it allows for the differentiability of the non-differentiability and so on. So their motivation was to have a rigorous proof mathematically of this fact. And in this process, they also have this, really to illustrate this, right? They had this example where you had really dust particles falling everywhere into the event horizon, if you wish. So each time a dust particle crosses the horizon, then you will get a non-differentiable crease after that. And they push this to the limit, if you wish, right? So then this is the nowhere differentiable horizon. So it is a mathematical thing, yes. But there's not to say that their motivation was pure, that the whole thing is physically not important. It is important, not in that extreme limit. So the reference is Piotr Krusiel from, I think, 2000.
Thank you.
Thank you, Guillaume, for your question. There are, I noticed a couple of questions. Lakshman, unmute and speak.
Yes, sir. Am I audible?
Yes.
Hello, Professor. So you said like this area increase law is within GR. So can we use this area increase law to constrain the posteriors, like to constrain more the posterior, because if it is within GR?
Yes,
like
I mean, the way that
parameter estimations.
Right. So if this parameter estimation, the natural thing you will get after choosing all the pairs of the parameter estimation, you will get this distribution, the posterior distributions on the change of the area, right? And then, it might happen maybe in the future that if GR is valid and you can actually measure this accurately enough that you do get significant violation of Free's law, then you can have the question, well, what theories would actually produce this? And that to me is not so clear. Of course, you can make some phenomenological arguments and you can say that something is happening at the merger which causes the area increase law not to be true. And the main suspect then would be sort of the energy conditions. You could have some flux of things falling into the black hole which do not satisfy the energy conditions. So that might lead to this decrease of the area. But it's not fully quantified. So I don't know, if you ask me precisely, what the alternate theories would be that leads to a decrease of the area. So I think that was a question, right? So I hope that answered what you had in mind.
No, I was asking within GR, like within GR we can use the like this area increase law having mass M1, M2 and MF and Chi1, Chi2 and Chi. So can we use these equations to constrain more the parameter estimation, the parameters there.
Yeah, oh, I see. So now, okay, as I understand now. So no, not really, because you can see it already from this argument by Stephen Hawking, right? So the result that he got for the efficiency was about 30%. And of course,
Okay.
the other way around is that the actual efficiency is much smaller. So therefore, this indicates that the constraints that you get from the parameter estimation of the masses is sort of more informative than what you get from the area increase law.
Okay, thank you.
Thanks, Lakshman. There's a question. Sorry, Badri, go ahead.
So I was saying there might be some configurations, I guess, where this may not be true, but often I don't know which one of those would be, but it's possible, but I think it's not so likely. So I think more likely is that the more informative constraints are on the masses and the spins, and then you can go back and sort of confirm on the area increase law. But the other way around seems more less likely to me.
Okay, there's a question in the chat. In fact, there are two of them. Ian, would you like to unmute and ask? You can do so if you raise your hand. Would you like to unmute and speak? Okay, let me read it out if I don't hear back from Ian. Ian asked, doesn't the assumption that the final state be a curved black hole restrict the class of gravitational theories already?
Yeah, so in some sense it does, you're right. So it might be that the observationally speaking, the Noether theorem is not satisfied in nature. Maybe it's a small deviation from that. So which is in fact why I said that if you can measure multiple ring down modes of the final black hole, then in fact you can independently confirm that the black hole is curved or not. Okay, so you're right. So it is an assumption, and the same is true for the initial black holes. So yes, I mean you can reduce the assumption by the extra observational result. It's amazing that you can hope to do all of this completely observationally, and if this prospect of this multiple ring down mode, which is a very interesting thing, and that I think actually will happen and actually has happened already. So if that is generally confirmed and accepted, then in fact you could drop this assumption. So you could do it in two steps. First, from the ring down analysis, you say that the final black hole is curved and what are deviations from it, and then if it is curved, then you can apply the area formula for the curved black hole, and then check the area increase law. Of course, you can ask the question, if it is not curved, what should I use for the area? So that's an interesting question. So I'm not sure what the answer to that would be. At least the first approximation, I think, still assuming the area formula is probably fine. But at least you can reduce that extra assumption by this procedure.
So there is another question. Just give me a minute. It asks, visualizing two horizons, let's say some kind of spheres colliding this law, A1 plus A2 less than AF, is always accomplished along the merger process.
So you want to visualize, I mean, I'll have some movies for you later, which was one of the goals of today's talk. So I will, hopefully by the end of this, you can visualize how this whole process happens. And
I think the question is it always accomplished along the merger process?
Yes, so within GR, yes, the answer is yes.
Okay, thank you. There are no further questions at this stage.
Okay. Okay, good. So let's go on. So this procedure has been applied to this first event. This is a nice paper by EC et al. From last year. So what they do is they truncate the in spiral at the merger, so which is taken to be the peak of the signal. And the ring down is then taken to begin either at the merger or let's say a little bit after the merger, right? So ideally speaking, of course, you want to be as far away from the merger as possible. So that would be the strongest test. But with the present observation, if you do that, then you quickly lose SNR. So you want to be close to the merger as far as possible in terms of getting larger signal noise ratio. But you should be aware that this could possibly lead to more systematic errors because the merger might complicate things, and that's where you expect the area increase law to be violated, right? So ideally, you want to leave a little gap at the merger. But still, I think it's a valid thing to do it this way. So they use a particular waveform model to analyze the in spiral. The details of that are not important. It's just to say that it's quite an accurate model, which is based on numerical relativity simulations. And for the post-merger, they use damp sinusoids because you expect there to be the ring down signal dominating. And they report at least 95% significance of the validity of the area increase law. So this is an example of what they did. So this is a typical waveform. And then before this part, the blue part that is using the in-spiral, this is using this the waveform model, this NR surrogate model. And post-merger, they use the damp sinusoids. And then this is the sort of the transition point between those two. And this is the result, a typical result that they find. And if you focus, well, for both of these is roughly the same. So let's focus on the case when there is no gap between the two portions of their truncated waveforms. So then with the procedure that I said before, you get the posteriors in delta A. This is what they get. And you get then the integral of this part of this is then quantified the significance. Okay. So this is a nice result. So this is the first published result where this was done. And the hope is that with future detectors, you get really much tighter posteriors, and you can either confirm or disprove this law to really amazing accuracy. And I think this will happen in the third generation detectors. So just a little word of caution here, which is that there's numerous systematic errors that affect these results. So we reported some of these towards the end of last year. So what happened? So some of the choices of systematic, some of the reasons for the systematic errors are the choice of the waveforms that you choose, pre and post merger. So in this, they pick one particular case, but there's also other accurate waveforms you could pick for the pre-merger. And then similarly, the truncation time, right? So you want to know after what time is the ring down description valid, and that gets us into questions about what ring down models and the question of the overtones or not. I won't get into that, just to tell you that there are sort of numerous choices that one could make, which are all reasonable. And depending on these choices, the significance of this test can be as low as 60% or thereabouts. Okay. So these are some examples of this of such effects. So these are, in this case, what I'm showing here are a bunch of results with the same in-spiral models, but at different truncation times and different models for the ring down, in fact, with different combinations of these damp sinusoids. And for various of these cases, you get, in fact, the significance can go down quite a bit, and in fact, even as low as about 60%. So just to say that, take the significance of this perhaps with a little grain of salt. But again, this does not distract from the fact that these kinds of tests will become more and more sensitive, and then you will really get, hopefully, a very accurate confirmation of this law or disproof of this in the next years. Okay. So that was the observational part, and I want to talk more about the observational side of things from now. So now we'll go to the theoretical side, and I'll talk about how do we formulate the area increase law quasi-locally. Okay, so I talked in the very first lecture about event horizons, but as you might expect, there's a nice formulation of all of this locally as well. So let me talk about that. So let me picture here a dynamical horizon. So again, recall that a dynamical horizon is a tree surface, which is foliated by these marginal surfaces. Okay. So we pictured that in this way. So you start off with S1, which is a marginal surface at an initial time. It increases in area, so it grows. So that is meant to be this portion here. And this portion is typically, well, almost always a space-like dynamical horizon. At some point after a time, after this time, it will settle down and you'll get an oscillator horizon. But this is not of this we discussed in the second lecture. So this is not our focus here. Here we want to focus on this portion. Okay. So now, given that this is a space-like surface, I have given to me then a unit time-like normal to this. I'll call that tau hat. And again, I have a unit space-like normal to the cross sections, which are tangent to H. So there is this R hat. Okay. And by combining this tau hat and R hat, I can get the N and the L, the null normals. Okay. So very similar to what I talked about in the very first slide, which on a given Cauchy slice, the same principle here. So what we have also is that we have the expansion of this L should be 0, and the expansion of the N should be negative. Okay, let's assume that is the simplest example here. And by the way, it should not surprise you that this is a space-like surface, of course. So then both L and N are both, if you like, pointing inwards in this example, right? The real thing is they're pointing to the future of the surface, but in this case also happens to be pointing inwards in this sense. So if this were null, then L would be tangent here, right? So this L is tangent to the horizon, but here the light cone is pointing inwards in this direction. That's why the L is here, and the N is even further inwards. So now let Q be the Riemannian metric. So it should be a Q tilde, I'm sorry. So Q tilde is a metric on cross sections of H, and tau and R are the unit normal and the radial vector. And let's say that this D is a Riemannian connection on H. So here now there are no complications with null surfaces. So given the 3 metric on H, I can easily construct its connection by the usual Christoffel symbol. So that's completely fine. And then we make this choice of the null normals, and then the area increase law is really trivial in this case. So the area increase law is controlled by this combination here, which is the divergence of this vector R. If this is positive, then it means that the area is increasing along R. If this is negative, it means it is decreasing along R. And you can simply write this R hat in terms of L and N. So this should be indices A here on the L and the N. But you can decompose the R in terms of the L and the N, and then you can simply recombine this in terms of the expansions. And then since the expansion of L vanishes, so then you can show that this combination here must always be positive. Okay. So therefore, in this setup, the area must always increase along this R direction. Okay. So this is sort of the first simple result you can obtain from dynamical horizons for the area increase law. So it's almost a trivial calculation. I can show it to you in just one line. So just from how the expansions are defined, you can show that the area has to then increase along this R hat vector. So now, of course, there are, you can include numerous complications. So even though this is physically, perhaps this is physically for our purposes, the most important example, and this is sufficient for us. But you can ask a more general question, right? So a dynamical horizon can be space-like, can be time-like, can be null. So therefore, how general is this? So can, in fact, you show a monotonicity of area in a more general setting? And the answer, in fact, is yes. So this is a very nice result due to Raphael Busso and Netta Engelhardt. So they had the first result back in 2015, and that's a more detailed paper just after that. So this applies to a dynamical horizon with arbitrary signature. So they don't need to assume that it is space-like. You have to make some different assumptions, which we will explore towards the end of this talk. But nevertheless, you have certain assumptions here. But you drop the assumption that this has to be of a particular signature. Okay. And also in their papers, you should be aware that they don't call these objects dynamical horizons, even though that's what they are. So they call them holographic screens because their motivations are somewhat different to ours here. But it doesn't matter. So it's the same object, more or less. So then we have a dynamical horizon in which I have, let's say, a parameter lambda, which labels my trap surfaces as this goes in one direction. So this may not be time itself. So this could be going along, lambda could be going along increasing or decreasing time. So it's not, so that's why you sort of introduce this parameter explicitly. So not to confuse with the time, it doesn't have to be going forward in time. Okay. So then it's a scenario here in which you have maybe a transition of the signature. The signature can be of one sign here, could be a different sign in this region here, for example. So you want to analyze this whole situation. So I won't go into details of the proof, and you can read the papers for that. But let me just tell the main ingredient of what they're doing. So the main object they consider here is this, what they call the evolution vector field. This is the analog of, if you like, this R vector here. Okay. So in this case, this R was a simple combination of this some L and the N. So in fact, we did that way. We had R and the L, R and the tau, and we constructed L and N. But in general, you will have some L and N, and from that, you need to construct some evolution vector along the horizon, which could be space-like, time-like, or null, right? So for example, here, if you do the same thing, so the evolution vector is precisely along L, so it is null. But there's other cases in which this R could be time-like, right? So you want to make it as general as possible. And so therefore you have a combination of L and N, which is all that you can say. And so you get a vector, which let's call it V, which is a combination of L and N. So which is sort of evolution vector along this parameter lambda on the horizon. Okay. So then the signature of H is then determined by the sign of the norm of this V. If the norm is 0, it's null. If it is positive, it is space-like. If it is negative, it is time-like. And you can calculate the norm from this L and the N. Then you can show that the norm is simply a product of B times C. These are the coefficients that appear here. And these are functions, in fact. Right? These functions will change, and their change will determine the change of the signature of the horizon. So then you have 4 possibilities, of course. So you have different signs of B and C are possible, and the combination tells you the whether it's space-like or time-like. So you can have the combinations of B and C being 1 positive and negative. So these are, call them 1 and 3. So in one case, B is negative and B is positive, or if C is positive and C is negative. And then you have the other cases in which both are positive or both are negative. So if both are positive or both are negative, then from this formula, you see that V dot V must be negative. So therefore, in these regions here, this V is time-like. In these regions, V is space-like. Okay, so any questions up to this point? This is a simple setup, but the details of the proof are then complicated, so it's a good time to stop and ask for questions.
Sumit, unmute and speak.
My audible, sir?
Yes.
Okay, sir, can you just please go back to the previous slide, back 2 slides?
Sorry, Sumit, I cannot, could you speak a bit
Yeah,
louder?
yeah. Can you speak a little loudly or closer to the microphone?
Yeah, sure. Can you just please go back to the previous slide? Yes. Am I on? Yeah. Previous 2 slides, I mean, one more slide back, please.
Yeah.
Yeah. So here, is Q tilde AB, what exactly is Q tilde AB?
Oh, yeah. So Q tilde IB is the two metric on the sphere. That's how the expansions are defined, right? So I have the spheres given to me. These are the marginal trap surfaces. So Q tilde is the 2 metric on those spheres.
Okay. So, okay, I understand. Can you please just go back to the previous slide?
So again, could you repeat? I couldn't follow.
Oh, yeah, sure. Can you just please go back to the previous slide?
By previous, you mean now previous year or?
Yeah,
here?
this one. Yeah, sure. Yeah, the dynamical horizons one.
Here.
The earlier one, this one. Yeah.
Yeah. So, in correspondence with the Netta Engelhardt, the Engelhardt and the Busso proof, you're saying that VA is the evolution vector, right? And the correspondence here with the dynamical horizon is the RA cap vector. Am I correct in this?
Yeah, so that is one example of an evolution vector, but this is just the space-like case, right? So what I meant to say was that their setup is more general. So you could have, in fact, the horizon being within the light cone. So it would be then in this direction. So then the combination of L and N, you can still find a combination that is sort of orthogonal to the leaves of the foliation, but then would not be space-like in that case.
But if RA is your chosen, evolution vector, after the situation goes down to the isolated horizon, the evolution vector, I think is, if I'm correct, is given by the LA vector, right? Which is the null normal to the isolated horizon. Is it so?
Yes.
Hello?
Yes.
So just at the point from the dynamical horizon towards going to the isolated horizon, this RA vector changes its nature from the space-like to the null. Is that a discontinuous change for the topology of this, dynamical? For this dynamical horizon into the isolated horizons. An abrupt kind of change in that.
Well, it's not a discontinuous change in the sense that, of course, we have defined R hat and L hat here and tau hat. That will not really be useful, right? Because this is quoted because in the null case, the tau hat is really not defined. Right? There's no unit time like normal to the surface. But you can find, of course, you will have a smooth vector which sort of goes here and along here, which would be different from R hat and L hat, but they're up to rescaling. But you can find a smooth evolution vector which goes transitions from space-like to null. So that you can do.
Okay. Okay, sir. Thank you.
So in this setup, right, so if you look at this B times L plus C times N, it's just that when either B or C, let's say when C would vanish, so then V is proportional to L in that case.
Yeah,
So that
sure.
is the case in which you are in the isolated horizon case.
Okay.
So, but
you,
it is
Sumit.
true that,
Sorry.
yeah, so just again to emphasize that this construction of the tau hat is not, you have to be careful with it. I mean, it can be done, it's not that difficult, but as it stands naively, this is not a useful thing in the null case.
Okay.
But there is a smooth evolution vector which will go from space-like to null. That is quite easy to achieve.
Mhm.
And there's no change in topology here. Right? Topology is always spherical, so that's all fine. So it's just that the you'll be careful with things being null and being time-like or space-like.
So the only requirement that we require of these evolution vectors is that it has to be transverse to these two-dimensional cross sections.
Orthogonal, in fact, yes.
Orthogonal, yeah, sure.
Thank you, Sumit. Yeah. Are there any further questions? Are there further questions? There are none at this stage, Badri.
Okay, good. So, right, so then you have these four situations, and then let's now talk about the area increase law that happens in these, the question is of transitions between these different regions, right? And that is when you can have possibly area increase or decrease. Within each of them, the area is monotonic, right? And how do you see that? Well, a simple calculation will show the following, that if you look at the increase of the area, so let's look at the Lie derivative of the area element on the spheres of these marginal surfaces, and as it changes, is a change along the vector V. So you can show, in fact, by a simple calculation, very similar to what we did in the very beginning for the space-like dynamical, a little extension of that, that in fact, the change of the area is given by an integral of this form in which you have the quantity C appearing multiplied by the expansion theta n. Okay. So let's also assume now that theta n is negative for the moment. Then everything is then determined by the sign of this quantity C. So therefore, if you have a transition from, let's say, between 1 and 4, C is still negative here. So that doesn't affect the monotonicity of the area change. And same thing here. You can go from 2 to 3. The problem is if you go from 1 to 2. So then C changes sign in that. And therefore, that is then the case that you got to worry, in which, well, then the area will be of one direction in one regime and of a different sign in the other regime. And the main result shows that the C, in fact, cannot change sign. Okay. So the details of the proof are, I mean, I can go through it if you wish, but it is a little bit involved. So we won't have enough time to do that here. So I'll just motivate you to look at the paper and to go through that proof. But the main result is that C cannot change sign. So therefore, transitions from 1 to 2 or 3 to 4 are not allowed. But, well, what are the assumptions in this? That is an important question. So the assumption, which is, in fact, which seems like a very trivial thing, and which is, in fact, is not true, which is not always true, which is that it requires the existence of at least one time in which C is entirely negative. Okay. So if for those of you who know sort of elliptic equations, so their result is based on a maximum principal argument. So that requires that, in fact, one time at which this C is entirely negative. And yeah, but apart from that, you have the energy conditions, and that the shear of L must not vanish analytically. So you cannot have these very non-geometric cases where the shear is entirely zero. Okay. So so with these assumptions and this assumption, which is existence of at least one time at which C is entirely negative, so with that you can show that the C cannot change sign, and therefore the monotonicity of area is then guaranteed. And again, we'll see a little bit later whether these conditions are in fact true for a binary black hole merger or not. Okay. So let me now change track a little bit. So again, even if you accept all of these proofs of the area increase law, so this shows you that the area of a dynamic horizon is monotonic. So will be increasing or decreasing depending upon what choice you make for the time. But still, can you go further? Recall that one way I criticized event horizons was that, well, you cannot have for event horizons a flux law which tells you that some stuff of matter falls in and that makes the area increase, and then you can link the area increase to fluxes, right? So that I told you that is not possible in general for an event horizon. It is possible perturbatively, and that's where the Hartle-Hawking result comes in, but it is not true in general. Then the question is, well, can it be done for these dynamical horizons? And in fact, it can be done for the space-like cases, which is, again, as I said, the most important ones for physical purposes. And this is a result we showed back in 2002 and 2003. So in fact, what you can do is you can write the increase in the radius. Again, by radius, I mean area upon 4 pi square root. So this is an increase of the area. So from one time to the other, so change of R from R1 to R2, you can show that it can be written as a sum of two different fluxes. So there's a fluxes due to matter and maybe due to radiation, okay? So it turns out, in fact, that you can write this area increase law in this physical process version. You can actually link the area increase law to these fluxes in this precise way in full exact GR with no assumptions and no other assumptions and no approximations. You can show that the matter contribution to the flux is given by the flux of the energy, stress energy tensor. So again, it is space-like, so there's a unit time-like normal to the dynamical horizon, so that is this tau hat. This psi is a vector proportional to the null normal L. So we're looking at fluxes along the L direction. So this is then a flux of matter fields along the L direction. And so this is positive if you assume an energy condition. Okay. So more interesting is the other case in which you have not the matter, but in fact, infalling gravitational radiation. So it turns out, in fact, that you can write the fluxes of radiation in this form here, in which sigma is the shear of the null. So let me go here. So sigma is a shear of L. So in fact, this term here, sigma square, should remind you of the Hartle-Hawking law, in which the area increase law was given by the shear square. So this is exactly in that same spirit. And this quantity zeta is a new effect here, which is a combination of the derivatives of L. So in this case, you take one derivative in an angular direction, the other derivative in the radial direction. Okay. So this term doesn't appear in the Hartle-Hawking formula and is usually subdominant. There's still some open questions about its precise meaning, but still it does appear here. And this NR is a suitable lapse function. Okay, so we don't need the details of that here. The important point is the following. So these are the few important points here. So these fluxes are all local. So these are calculator fields on the horizon, so like the shear, like this quantity zeta, and what have you. So it doesn't refer to anything happening in the future. So it's not teleological like for the event horizon. And secondly, and perhaps most striking, is that these are all positive definite. So these things are manifestly positive. So it's a square, and this term is positive if you assume an energy condition. So therefore, this is the change of the area is sum of positive terms. So therefore, the area has to then increase. Right? So that is sort of the analog of if you use the Bondi mass loss formula at infinity, in which you have energy being lost by radiation, and that reduces the Bondi mass. So this is the exact analog of that here. So these fluxes, again, are independent of coordinates. So these are geometric quantities. So except again, for this important question of if I change my gauge conditions on the time slices, then you get a different dynamical horizon. But for each of these horizons, they're space-like, this flux law holds. Right? But within each dynamical horizon, it is completely gauge independent and coordinate independent. The condition of the expansion vanishing is critical. So without that, this would not be positive. So then you get additional terms, in fact here, which spoil the positive definiteness of this quantity. And then finally, this radiation term vanishes in spherical symmetry. So, and the reason for that is that if you're exactly spherically symmetric, then you don't have any symmetric trace V tensor, which is non-zero. You don't have any vector which is non-zero. Then it comes spherically symmetric. So in spherical symmetry, then this is exactly zero, which as we expect from gravitational radiation. And finally, as I mentioned before, this is consistent with the perturbative analysis of Hartle-Hawking. And in fact, you can also do a perturbative analysis for dynamical horizons. And that was done by Booth and Fairhurst, again, about 20 years ago. And they found, again, consistency with this result here. So it checks a number of these conditions that you expect for the flux laws, and they all hold. So, and there's, of course, future tests that you can do, and there's future work that is ongoing by a number of people on analyzing this numerically. And yeah, so I think this is then a nice formalism that is, I think, can be useful in these studies. So any questions on this part? So I just want to sort of mention this here. So it's an important result which shows that the quasi-local cases, you do have this physical process version of the area increase law. Okay. So any questions, any discussion on this, on these points?
Yeah, there is a hand raised, just bear with me.
Am I audible, sir?
Sumit, yes, go ahead.
Okay. So, I mean, why do you assume for the dynamical horizon also the theta L is equals to 0? I mean, you said that this condition is important for the...
Sorry, Sumit, could you repeat that? You're a bit faint.
Yeah.
Why is theta L is equal to 0 assumed even in the case of the dynamical horizon?
Oh, theta L is always 0, right? So this is the key case, right? So the I thought it was called theta N. So recall that this is the setup here. So we have the L and the Ln vectors, and on each of these cross sections is a marginally trapped surface, which means that the expansion of L vanishes. So that we always need. So what I meant to say was that it's not true in a general space-like surface with any foliation by spheres, with no condition on theta L. So you need that.
Okay.
Thank you, Sumit. Yeah, go ahead, Sumit, if you have another question.
Oh, sure. I got it, sir. No further questions.
Okay, thank you. There is a question from Oindrida, which asks, why is the matter flux calculated in the direction of L and not N?
Yeah, that's a good point. So I think you can choose different components of the flux for the fluxes, it's true. Then you'll get different flux laws. In fact, Eric Gorgolon and Harami had a paper on this topic, so you can take different directions for that. But in the end, you do get, again, flux laws of similar nature also for the other directions. In this case, this was sort of nice for other reasons, and we made a choice. We said, okay, let's do it along L. So the first time this was done. But yeah, you could choose different fluxes, yes.
Are there any further questions? Please raise your hand or leave a message in the chat. There are no further questions.
Okay, very good. So now let me present, to conclude this lecture, let me present some numerical results on all of this so that you can visualize what is happening in the black hole merger, and then we can understand the status of the area increase law in that case. Okay. So these are all results by Buchholz et al. From last year and from the last 2 years. So we're looking here at cases in which I have two black holes which are merging, and these are quite high accuracy simulations. So, and in fact, we have the important feature here, which is not true for most other simulations, is that we have an extremely accurate numerical method for locating these marginal surfaces, which works in extremely distorted cases as well. Okay, so we're applying this to a simple case, so which is two black holes which are non-spinning and which are starting off at rest and merging head-on to each other. Okay. And the initial data in this case is time symmetric, so by which I mean that the extrinsic curvature vanishes, and it's also conformally flat. So the 3 metric, which again I'm calling Q here, is given by the conformal factor multiplied by the Euclidean metric. Okay, and the conformal factor here, this is the Brill-Lindquist data. So this is of this particular form. So what R1 and R2 are, these are, so you have to imagine that you have Euclidean space, just R3, but you have some 2 punctures on the space. So, and these are, and you measure distances of any point on the space from these 2 punctures. And these distances are R1 and R2. And the conformal factor is given by this expression here. So with M1 and M2 being the bare masses of these two punctures. Okay. So it's a very simple setup. So it hides a lot of sort of non-trivial information, but at least the initial data is extremely simple and it's easy to write down in this very short way as well. So once again to repeat, so non-spinning black holes, initially zero momentum and colliding head-on to each other. So this is what then happens. So let's assume that it start off at a very early time. So at very early times, so if you start off with a large separation between the two black holes, then you just have the two horizons which contain the two black holes, the two punctures, okay? As these punctures move in, what happens is that there's a new horizon that appears outside both of these individual horizons. So in this picture, what is shown are the red ones and the purple ones are the two individual horizons, S1 and S2. But when the black holes get sufficiently close to each other, you have a new horizon that appears and that bifurcates into an inner component and an outer component. So you have the outer component that is shown in blue here and the inner component that is shown in green here. Okay. And the evolution proceeds. And at some point, these two horizons, the S1 and S2, they come and touch each other. But what happens in this touching process is that the green one, which is the inner common horizon, that gets extremely distorted. So it has a kink almost at this point, just close to the merger. This is a close-up of what is happening at the merger. And the green one is this extremely high curvature neck here, exactly at the point when the two S1, S2 are about to touch. Okay. But more importantly, for physical purposes, the outer one, the blue one. So that is the one that forms when the two black holes get close to each other, and that then grows and settles down to an isolated black hole at the end. So let me in fact show this in a movie. So this might sort of make more sense visually for you, right? So this is the question that you asked, somebody asked in the beginning about how do you visualize these two black holes that they merge and that you have two horizons which touch and they merge and the new horizon forms. How do you visualize that? So let me show that here. So let me first stop sharing this screen and share the screen of the movie. And so just bear with me for a minute. Where is that? Here. Okay, can you see the screen?
Yes, we can.
Okay, so let me now play this movie, okay? So let me just tell you what you're gonna see. You're gonna see these two black holes, and we are tracing out the world tubes of these horizons as they evolve in time. And these are precisely dynamical horizons now. So each of these cross sections is a marginal trap surface, and it evolves in time. And you'll see how this evolve and they behave as the evolution proceeds. Okay, so let me show that to you here, and let me. So you should see now that these two horizons, these are the two individual ones, they evolve in time and they trace out these beautiful dynamical horizons. And at some point they come close to each other. And we'll stop here. So let me then, I will just stop here. Okay, so let me just stop here. So what is done here is that when the two black holes come close to each other, at this time, a common horizon forms, okay, which is outside these two individual horizons, the purple and the red one. The blue one is the one that moves outwards, and the green one is the one that moves inwards. Okay, so it's a bifurcation. And now we will trace the blue one as it evolves in the future in time and settles down to equilibrium. Okay? So that is this one here. And again, this is a beautiful isolated horizon at late times. And well, what happened its side now is the other question. So recall, let me just, before I play the future, let me once again play this in the past. So the green one is the one that moves inwards and gets these extremely high curvature regions at the merger here. Okay, And we'll see later on in this movie, we'll zoom into that part and see what happens at this merger for the green horizon.
And the two black holes are assumed to approach each other radially?
Well, they do approach radially, yes. So this is the calculation in full GR. Yes, so this is, yes, so just to answer your question, yes, the two black holes approach radially, so this is the head-on collision, but the same generic feature should be valid also for other cases as well. So that is ongoing work, but I don't expect any surprises on that point. So what happens is that the green horizon, the one that is coming inside, so that develops these kinks and these self-intersections. Because as these two individual horizons, they touch and they penetrate each other, something has to happen to the green one. It's not that it ceases to exist, it exists, but it developed these extra self-intersections at this merger. Okay, so that was the whole thing. So let me just, I like it so much, let me play it again. So let me just play that once more, just so you see the whole thing once again, without any interruptions from me. Okay, so this is a beautiful movie made by Daniel Poole, the main author on these papers, and I think illustrates very nicely the geometric picture that we're seeing here. And this is sort of a picture of the whole thing in a graphical form. So these are the different things that are happening here. So we have, again, as I said, let me just repeat. So we have the two horizons that evolve in time, trace out these dynamical horizons, and they come closer to each other. At a particular time, which let's call it T bifurcate, a common horizon forms. One portion of, so one branch of that moves inwards, the other branch moves outwards, okay? This transition here is completely smooth. So it's like a parabola, which is being sliced in different ways, okay? So like a quadratic function is what is happening at this point here. So the outer one is the physically important one that goes outwards and settles down to an isolated horizon. The inner one merges with the two individual ones. And at this time, let's call it T touch, is when the two individual horizons touch each other. At that point, this inner horizon develops a kink, and beyond that time, it develops self-intersections. Okay? So is this picture clear? So any doubts on this sort of visualization of this merger process?
Are there any questions, students? Yes. Etsushi, please go ahead.
Yeah, hi. Am I audible?
Yes, you are.
Yeah, so I didn't understand this bifurcation, like why is it happening? And also if you could relate this diagram with the one which you showed for dynamical horizons.
Okay,
just
good.
yeah.
Yes. So you mean this diagram I showed in the beginning, right? This one. Did you mean to do this diagram to relate?
Yes, this one.
Okay. So this picture here is sort of a single dynamical horizon. Okay. So if you go back to this picture here, this one here, each of these individual ones is one of these. You should imagine a picture like the diagram I before for each of these ones. So there are 4 of these here. Okay. So there's the individual one here, this one, there's this one, there's the outer one, and there's the inner one. Okay. So I'll come to the question of why the bifurcation happens, but at least it should be clear what these 4 different horizons are in this case. In fact, you could even view these. Yeah, sorry, go ahead.
No, so as in this common horizon that is forming, like I didn't understand. It's part of the dynamical horizon, or like again, like I didn't really. I'm not being able to relate it with the figure that was previously shown for the
So
dynamical
that
horizon.
figure, so you, okay, is it clear for the for individual horizons what that figure is, right? So these are the world tubes, and you have the null normals. Of course, you can construct them here, and they'll be as in the diagram showed before. Okay.
Right.
So this outer one, you can again imagine that if I forget the bifurcation thing, I just look at the blue one, that is again of the same form like in the diagram.
Yeah.
And the same thing is true for the inner one, for the green one. So in this, if you wish to interpret it like this, there are 4 different dynamical horizons here. So there are the 2 individual ones, and for each of them, a picture like this you can draw, like this. So imagine this is S1, S2, you repeat this twice, right? There's 2 of these that are coming close to each other and merging. Okay. And then similarly for the blue one and for the green one, you have the same picture as well. So you have, in fact, 4 of these dynamical horizons in this picture.
Right. Right. Okay.
Okay. But there's not, in fact, 4. In fact, as I said, this bifurcation is actually completely smooth. In fact, so if you were to sort of take the union of the blue and the green one, so it is just one smooth surface, in fact. And you can take that smooth surface to be a dynamical horizon. And along that surface, you expect that the area should behave in the following way. As I go backwards in time on the green one, the area will increase because the green one has decreasing area as it goes forward in time, with an important caveat that I'll mention in detail in a minute. But at least for most of its existence, so the green one is decreasing in area as I go future in time. So if I go in the following direction, I go backwards in time on the green one, I reach the bifurcation point, then I go forwards in time on the blue one. In this whole process, the area is monotonic. And in fact, everything is a smooth surface. So it's a smooth dynamical horizon with monotonic area change.
Right. And
Thank
this
you.
this
Go ahead.
blue horizon then eventually evolves into an isolated horizon.
Exactly, yes. So this is the one that, for astrophysical purposes, that is the one that is important. This is the one that will approach the event horizon. And this is the one for which you can do all of black hole spectroscopy and things like that. So this blue one is the important one.
Right. Okay. Thank you. Also, where can I find the link for this movie?
Oh, I can send you. Okay, I can send the link to Chandra and to Sriram so they can post it on the webpage.
Sure. Sure. Thank you.
There is another question, Badri. Kaushik, can you unmute and speak?
Yeah, am I audible?
Yeah.
Yes, you are.
Yeah, so Professor, I have a doubt in the part where the 2 horizons touch at t equals to t touch. So after that, what happens? Like they form a kink, and like the green one stays at least as it is. Like they do not
Let me
come
explain.
to a common thing. Yeah.
Right. That's an important question. So let me explain that in a minute. So let's see if I have a good figure for that. Okay, so let's look at this picture here. So this is a close-up of the place that they are touching, of they're intersecting each other. Okay. At a particular time, at t touch, the purple one, that is one of the individual horizons, and the red one is the other one. They are just touching each other at one point. Okay. And beyond that point, they start going through each other. So that's why in this picture, there's a bit after t-touch. So in this one, the purple and the green one and the red one, they're penetrating each other. So this extends to a big sphere here, and this one goes to a big sphere. There's a close-up of that intersection. Okay. But what happens to the green one is interesting. At the moment that they touch, so the green one is also touching them exactly at that time, and it has a kink. Because when 2 spheres touch, at the point of touching, there's a sort of a discontinuity there, right? It's a cusp. So the green one has a cusp exactly at that point, and the green one doesn't cease to exist beyond that point. It just evolves in this particular way, in this it develops these loops, and it evolves. It continues to evolve in the future, and the loops just grow in size.
Okay. So the thing is that after t-touch, both the green ones will settle to a common thing, or they will remain as it is?
Yeah, the future end of the green one, we don't know yet. The simulations lose accuracy as sort of things go really into near the punctures. So this is what we know at the moment, that the green one, there's only one green one. So it develops a cusp, and then beyond that, it develops the self-intersections. But the end fate of this, we don't quite know.
Okay, thanks a lot, Professor.
Thank you,
Actually,
Kaushik.
nice follow-up by Daniel and other co-authors, in which they sort of find other horizons here in which you have multiple topological features. So that's a nice feature, in fact, of WhatsApp. So I should say, so let me correct myself. It's not that we don't know. We do in fact know. It's a more complicated picture, and I don't have the relevant figures here, but I can present the references in the slides later on. So it's a very nice picture in which you have a lot of these green ones, they combine, and there's multiple self-intersections, and at a certain time, a later time, the green ones all annihilate each other, and so those are more results. So, but this is the one that I know much better. So at this stage, this describes at least this intersection process.
There is one more question. Lakshman, can you unmute and speak?
Yes, sir. Am I audible?
Yes.
So, the law is valid for means at any instant, or it is for the final thing only? And if it is for any instant, then in that case, the A final is the green one or the purple one?
Oh, here these are the surfaces. I'm going to talk about the area increase law in a minute. But at this point, these are just the surfaces. They are just the shapes of the surfaces here, right? So to get the area, I have to compute sort of I have to integrate the area along all of these surfaces, and that I will show you in a minute what they are. But at this point, these are just the geometrical surfaces that evolve in this particular way.
Okay, so that means the area law is for the final thing, not for the dynamical thing.
No, it is better than that. So I will show you in a minute.
Okay.
But there are subtle aspects here, but I will show you what happens to the area law.
Okay.
There is one more question. Srijit, please unmute and speak.
Yeah, thank you. What would be the tangent or normal to this green surface in terms of A lane, R, and tau?
Oh, okay. Well, it's hard to visualize that in this, but you can visualize the radial. Yeah, okay. So let's go here.
Okay.
Let's see here, right? So there would be a radial evolution vector here, right, which is tangent to the surfaces.
That is R, I think.
That is R, yeah.
Right. Okay.
So that is the easiest to visualize here also.
Yeah, but for green one, can one? It is not very clear, right? Okay.
We can construct the R, right? So evolution vector is easy, right? So it is the vector tangent to these surfaces and along the surface.
Okay. And another question is that what determines this T touch, that epoch when it touches? I mean, the initial data itself or something more? I mean, this time epochs can it be predicted from the initial data itself, or it?
Yeah, I think we should be able to, we haven't done that yet, but you should be able to predict it. So essentially it is, if you have, of course, if I start the two black holes very far away, so there should be a relation between how far away the black holes are and what T touch is. So I think that can be done. I think, yeah, I expect there to be a nice prediction of that. Yes.
Okay. Thanks.
Badri, I have a naive question. The inner horizon forms because these are isolated horizons. There wouldn't be such an inner horizon if there are two black holes merging.
Sorry, Sriram, you dropped out for a few seconds. Could you repeat that, please?
Okay. Yeah. I was asking whether if the inner horizon arises because we are considering isolated horizons here. And if I have two black hole horizons merging, would there be an inner horizon in that case as well?
Oh, these are dynamical. These are not isolated, right? These are isolated only at the very end and maybe at the very beginning. Whole life, they are completely dynamical. This is in full GR now. This is a numerical simulation solving Einstein's equations, right? In full. So here, these horizons are time dependent, so they're changing in area. And as I'll again mention in a minute, so these are fully dynamical here. So there's no assumption here on that front. So these are in fact two black holes merging, right? This is the picture that you have in terms of these marginally trapped surfaces.
But the conventional pictures in the spans mode will indicate essentially the outside horizon. Am I missing something? I'm concerned about the formation of an inner horizon. Is that understood?
Yeah, so it will. It is this bifurcation process, right? So I mean, the point is that these horizons do not disappear and appear out of nowhere. They always appear in pairs. So it always appears as inner and an outer pair, and the whole thing forms a smooth surface. So it is sort of a result of the smooth evolution of these horizons. So you can't have one just disappearing and one just appearing for no reason.
Okay. Maybe I'm missing something. I'll try to understand. Thank you.
Okay, so now let's talk about area increase law. Okay, so let's draw the areas in this way. So first of all, let us take the sum of the individual. This is not time, and these are some areas plotted here as a function of time. Okay, I'll explain what these different functions are. The first is very easy. The first is sum of the areas of the two individual horizons, and they increase in time, and nothing is unusual here. Okay. So in this picture, what is done, I just take these two individual horizons and just calculate the area of these software at any time, and we just add them and then plot them as a function of time. Okay, so that is this red dotted line here. And then I have, starting from T bifurcate, I have the blue one here. So this blue curve is the area of this blue surface as a function of time. So that is increasing in time, and it settles down to a constant more or less by this time. Then the green one is the area of the inner horizon here as it evolves and gets closer and closer to these two individual ones. So that is this green one. So it decreases in time initially here. Okay. Is that clear? Is at least I hope there's no confusion on what these different curves are, right? I hope if there's any, then please ask now. So a lot of people asked about the areas of these surfaces, and this is what it is showing. I'll explain some features of this in a minute, but I want to be clear that I hope that you understand what these curves are.
Questions, students? There are none.
Okay, so I hope it is clear. Yes.
I believe so. I believe so. There are no questions, so I believe students are fine.
So then you notice this green curve is sort of the complicated one, right? So the others are sort of as you expect. So the blue one increases. The red one also is always increasing, or at least never decreasing, right? And the green one seems to increase backwards in time as you expect. So if you connect this to the outer one, there says monotonic area increase as you go from here and trace it all the way back into the future. Okay. But at this point, it's not quite clear whether the green one actually is monotonic or not. I mean, if it really were decreasing, it has to sort of slope down always. It seems to be increasing here. And in fact, that is true. So if I look now very, very close to this point, exactly near here, so the green one, in fact, is not monotonic. So it is decreasing, and then it has a minimum, and then it starts to increase again. Okay. So then you can ask yourself, well, the green one is a dynamical horizon. Then the question is, why, in fact, is the area not monotonic? What went wrong in the Booth-Engelhardt proof of this? So if that proof of the conditions, the proof itself is correct, of course, the assumptions are, which of those assumptions went wrong, and why is this area not monotonic? If it were monotonic, what I had expected before I saw this graph was that this green one would always go down, would meet here, and then continue to go down. But in fact, it has a minimum, and then it starts to increase after that. And what is happening, in fact, is that the condition that there is so the problem is that the signature of these world tubes is not a fixed thing, is not a constant. So the different portions of the world tube which are time-like and space-like, and in fact the condition that this function C had to be there had to be one slice where C was always negative, that is the one that is violated. So you can find sort of those pictures in the publications, but that is what is going wrong here, okay? So the conditions, the assumptions of the proof are not fully valid. It is true everywhere that is interesting, so it is true all of here, but exactly near this kink is where things start to go wrong. So if you like, if you're deep inside the black hole region, then strange things happen, but at least for the physically important ones, things are sort of as you expect, and you can really understand the area increase law in this picture, in this formalism. So I'm almost out of time, so I'll close here. So as I said, so the area increase law is seen not to hold for the inner horizon. There's no contradiction with the Bousseau-Engelhardt. Well, the contradiction is the condition in the proof. It is not, the proof is wrong. It's simply that the condition, one of the conditions is not true. So the lesson here is that seemingly reasonable conditions mathematically do not always hold. And black hole mergers are one place where you can find strange things happening. So let me then close the lectures. I can say that we have covered a very small set of results connected to black hole physics and thermodynamics in these 3 lectures. I hope to give you at least some flavor of this approach to black hole physics. And the approach and the work over the last like 2.5 decades has shown that almost all aspects of black hole physics can be described quasi-locally. There's numerous open problems, mathematically, numerically, and observationally for in this formalism, and this has implications for black hole physics. Okay, so thank you, and I'll take any more questions if you have.
Thank you very much, Badri, for your lectures. Questions for Professor Krishnan, please. Any questions?
Can I ask one?
Sure. Please go ahead, Sri.
Yeah. So, Professor, can you go to the last figure that you showed?
This one?
Yeah, this one. Yeah. So, what can we say about the hierarchical mergers? Suppose initially 2 black holes merged, and then the remnant black hole again merging with another black hole, right? So, for that case, also all these things holds, right? I mean, all the.
Indeed. I mean, in that case, that's why I said that the blue one is the most important one, right? So imagine now that you take this forward in time further. So deep inside the black hole region, I mean, all of these will annihilate each other and they'll disappear. What is left is the outer one. And that will then become one of these individual black holes for the next merger, if you wish, right? So, or if you like, each of these 2, if you follow them back in time, maybe they were from a hierarchical merger. So at some point, that would be what is the blue horizon here. For the previous merger, this thing would be the equivalent of that horizon.
Okay.
So this picture
also,
is completely fine, but this is what.
Okay. And also, I couldn't understand why the green one should increase further. Can you again please repeat that? The green thing.
You're asking why the green one has an increasing area?
So yeah, from the figure, the later figure. So
this figure, you mean?
Yeah, last figure. So again, after reaching a minimum value, the green one will again increase, right? From the figure. So can you repeat that? Why it is happening?
Yeah. So the reason of why it is happening is not clear to me. It happens as an observation. So, and then the reason it happens is, well, the reason that. So I was trying to say that the reason that the Bousseau-Engelhardt proof doesn't apply here is that in their proof, they require this condition. So let me just go back to there. Yeah, so they required the existence of a single leaf of the foliation of the Dynamical Horizon, where this function C was entirely negative. So what happens is that there's a small portion of the whole surface where C is not negative. Okay? And that is what causes the proof not to apply fully. So the details of this, unfortunately, will take me too long. So I then have to go through what the proof exactly was, and that would require an entire lecture by itself. But again, this is the condition, and because the C is the thing that controlled how the area was changing. That is what appeared in this indicator.
Okay. Thanks a lot, Professor.
Thank you, Sriji. Any further questions? Any other questions? I don't see any further questions, Badri. Thank you. Thank you very much for your lectures. I should thank you on behalf of the Scientific Organizing Committee, the local organizing committee, as well as the participant. Thank you very much.